We continue with the previous lecture on stability analysis. So what is stability? In this lecture, we discuss on what is stability, why it investigates stability, examples of unstable systems, then route the stability criteria we discuss upon. Okay. So what is stability? Process to find out if the system is stable or not is known as stability. Okay, a system is stable if a system is stable if every bounded input yields a bounded output. So that is the first point. Second, a system is unstable if any bounded input yields an unbounded output. Then the system is called as the unstable system. Right. So why investigate stability? Most important issue is design a control system. It is the most stability is important factor to design a control system. Second one is an unstable feedback system is of no practical use. Unbacked system is of no practical use. Second one is a stable system should exhibit a bounded output if the corresponding input is bounded. Then one famous example of an unstable system. Look into this bridge above picture. So this picture shows the state of the bridge before the accident met. Okay, dramatic photographs showing the collapse of Tacoma Narrow Suspension Bridge in 1940. So it's a suspension bridge. So the first photograph showing the twisting motion of the bridge center span just before failure. The bridge started twisting. It shows it is an unstable. It is an unstable state. So what happened? A few minutes later, after the first piece of concrete fell, the concrete structure itself gets collapsed. The second photograph shows a 600 feet section of this bridge breaking out of the suspension span. So 600 feet of the bridge broken down. That concrete structure broken down. This one half is remaining. The remaining second half is breaking down. The second photograph shows 600 feet section of the bridge breaking out of the suspension span and turning upside down. Upside down as it crashed in Puget Sound in Washington. So this is a state of unstable system. Look into this time response characteristics and explain. Right side is real part, positive side of real part, negative side of real part. Top is positive side of imaginary part, bottom is negative side of imaginary part. If we look into this, the right side of explain, if the poles and roots present in the right side of explain, then the system is unstable. Then look into the second picture, second half, left side. The poles and zeros are present on the left side of explain, then the system is stable. Right. Then what is stable system? The natural response approaches zero as time approaches infinity. Natural response approaches zero as time reaches infinity. At infinite time, the response comes to zero. It is stable. It is stable. Okay. The oscillations are diminishing. Right. Now for unstable system, if the natural response grows without bound, if the natural response grows without bound as time approaches infinity, the natural response grows without bound as time approaches. Grows without bound. Okay, at when time t equals infinity, when the response goes to infinite phase means this increasing means it is an unstable system. Then what is marginally stable? With the natural response, neither decays nor grows, but remains constant or oscillates at time. It's infinity. Okay, just it is oscillating, and it is oscillating, and without just it is oscillating without moving above or below or a particular value. Then we call that as marginally stable. The roots and poles um, lie on the imaginary axis. Then we call the system as marginally stable systems. Contributions of the characteristic equation roots to closed loop response. So it is based on the roots present on the left side of real axis. Then the system is stable somehow. Then if it is on the right side, then it is unstable. Roots lies on the positive side of real axis. Then the system is unstable. Then if the roots present with negative real part and imaginary and negative real part and imaginary roots present on the left side, then the system is stable. Then the next one, fourth one, if the roots present on the right side of S plane and with the positive real part and imaginary parts, complex roots, then the system is unstable. Then the system is unstable. Okay, so we can find stability based on the poles, location of poles, and location of roots. Thank you. Thanks for watching. We continue route criterion in the next class.